Newton's first law. Newton's first law says every object remains at rest or in uniform straight-line motion unless it acted on by an unbalanced force. Unbalanced force means it's just there's a net force. The forces are vectors. Okay, if there's no force, then there's no unbalanced force, and then the object will stay the way it is. Okay, if it is at rest, it will be at rest. If it is in a straight line motion, and it will be in a straight line motion continuously. If there's all the forces are balanced. Okay, the first part is very easy to understand. If it stays at rest, if you don't bother it, and then it will be staying. The second part require a little bit of thinking. Then if it's already in motion and it will continue in motion, and then it will not stop. But that's sort of like a counterintuitive and also against our daily experience. Nothing really moving forever. But that explains that there's always some force on the object on the Earth. So, for example, you throw a soccer ball in the air, supposed to be going in a straight line, but there's air resistance and the Earth's gravity pulling it down and it hit the ground, then there will be friction and it will slow down. But if you really throw some object into the outer space, that soccer ball will moving in a straight line forever. Newton's second law of motion says that, well, if it really is an unbalanced force on an object, the object will start move or start accelerate. Okay, not just move, start increasing its speed. The acceleration is actually a vector, which means it has a direction and a magnitude. So officially it is said the acceleration of an object is directly proportional to the net force acted upon it, and inversely proportional to the mass. So the second clause is saying the mass of the object also matters, is how hard it is to get the object accelerated. So that's the second law. Well, if I ask you to say in your own words what is acceleration, you will say, well, the stronger the force, the faster it's accelerating. Okay, and also the heavier the object or the more mass of the object, well, it's harder to accelerate. So putting in mathematical form, and I would say it is like putting in mathematical form, I would say acceleration is actually proportional to the force. All right, so the inversely proportional to the mass. So right like this, or even though sometimes people would like to write this, F equal ma. So you see some posters, you will see this. So of course this just one manipulation of the term away, so you can just get this from here. You can derive this. Simply you multiply the m to the other side, you can F equal ma. So then we will use this formula. So if you have force in units of newtons and mass in units of kilograms, then you can calculate the acceleration in meters per second squared. Is our first question. So what is acceleration? And 1,000 kilogram car, if 5,000 Newton force was applied to it, what would be the acceleration? That would be straightforward. Apply the Newton's second law, the formula. So and 500 kilogram on the times meters, and 500 newtons. So that's the 5,000. That's actually the newtons. So and in fact, even though this is correct, but newtons, and that's kg, and then you will have this, okay, 5 meters per second. In other words, the mass, of course, is simply trivial, and you just need to understand that newtons is the force units, 5,000, and kilograms is the mass. So you see you get a 5 meters per second. The physical interpretation of this is the car will be moving, increasing its speed 5 meters per second for every second. So therefore, the acceleration of the car is 5 meters per second squared. Okay, most common acceleration phenomena you see, of course, is the car speeding up and something, the drop, free drop, and then that is under the acceleration of a gravitational force. Every object on the Earth's surface will sense a force pulling downwards towards the Earth and by the Earth. That interaction, that force between object is called the gravity, okay? Gravitational force. In other words, every object will attract every other object. Its intensity or the strength of the force is proportional to the mass of the two objects, and of course inversely proportional to the distance between objects. That's the gravity formula. That's called the universal gravity. And that force causes the acceleration. Okay, and for that, how strong the force attract, how strong the gravity is on different planets, it depends on how heavy the object is, how heavy the planet is. So therefore, just compare on different planets, you have different gravity, simply because the planets have different mass. So if we assume 1, okay, of the gravity, which means the acceleration, and this is just for the comparison, okay, and on the moon is 1/6 of it. It's like 0.2, okay, 0.19, very small. Okay, on the Mars is smaller. So by just looking at the gravity, you know how big the size, how big the size and the mass of all these. So from here, what is the smallest planet? Obviously from here, Mars. Oh no, Pluto is very small. Okay, for example, if you're standing on the Pluto, you can jump up like maybe 500 miles. You jump up. Okay, but on the Earth, you can jump only like 3 feet. Okay, on the Jupiter, you can hardly jump like 1 centimeter. So because it's heavy. Okay, so that's the gravity. Simply because these planets have more mass. Okay, mass also. What's the relation between mass and inertia? So inertia, okay, here is the tendency of object to remain in unchanged motion in the absence of unbalanced force. Inertia is actually proportional to the mass. Okay, but if you're really picky about what is mass, well, in a simple sense, you can say, well, the strength of inertia. In another sense, if you're a chemist, well, you can say, well, how much stuff is in there, how many neutrons or protons of these elementary particles are there, because they are all the same. Okay, so you can say, well, mass is how much stuff in there. And then every object on Earth experiences an attractive force from Earth. It is called a gravitational force. And in fact, that gravitational force is called the weight, how heavy it is. So we feel with our hands the weight, because we use our hand to balance the gravitational force on the object. So that the object is not moving, so we use our hands to feel the gravity, because we balance the gravity. So the weight is a gravitational force from the Earth. Okay, but now, and of course, and what is the, if you experience, we talk about the acceleration. Gravitational acceleration is 9.8 meters per second squared. So then the mass of the object times the acceleration of the object is the force, is the gravitational force. But the gravitational acceleration, as we know, is 9.8. Since we sort of retro back, we argue it back. Since this is the acceleration, and they multiply with the mass, that must be the force, gravitational force of the weight. So therefore, sometimes we confuse the word weight and force and mass, because we have excuse to be confused, because they are proportional. Okay, the more mass, and you have more weight, and even more mass, you have even more weight. Simply you multiply this by this constant. But mass is a mass unit. Weight is a force unit. Weight is more, their relation is weight equal mass times g. The acceleration is called gravitational force. So we will have quite a few exercises to stress this. Okay, and once again, weight is the gravitational force and mass is the mass. On different planets, the same mass will have different weight, but mass is never change from one planet to another place. Normally, it's never change. Here comes the exercise. What is the weight of 5 kg object? Mass, weight, what are the differences? So first, mass is the inertia or how much stuff in there. Weight is the gravitational force. So since the gravitational force, the weight is nothing but the gravitational force is mass times g. So then 5.2, that's the mass. Okay, and since every object will accelerate on Earth's surface with this acceleration, okay, therefore the force must be this many newtons, so 9.8 meters per second squared. So then that will give you a number of 50 newtons, 50.96 newtons. Okay, newtons. So therefore, this is the mass is in the units of kilogram. The acceleration is in the meters per second squared. So in fact, this defines Newton. So that defines Newton. So that's how mass related. This exercise is trivial, but important. Let us sort of differentiate the concept of mass and weight. Okay, the second and the third question are directly application of Newton's second law. What is the resulting acceleration of an unbalanced force? Remember the unbalanced force. You may have multiple forces on an object, but you cannot just count the result of one force. You have to have a combined result. You have to add those forces together as vectors, and with unbalanced force, that causes the acceleration. So the unbalanced force, this is the direct application. So acceleration is simply equal to the force divided by the mass. So then the force is 100 newtons and the mass of 5 kilograms, 5 kg. So that will give you a 20 meters per second, 20 meters per second squared. So that's the acceleration. Acceleration, in other words, you have an object, okay, 5 kilograms. It's like 10 pounds. You're pushing with the force like 100 newtons. That's about 10 pounds. Okay, and you push that, and this object will accelerate at this rate, which means its velocity will increase 20 meters per second each second. Therefore, 20 meters per second each second squared. Another side point, if I ask you, since weight and mass are different, they will say, well, what about 1 kilogram mass? How much force will be sensed by the Earth or applied by the Earth on the gravity? So then to calculate that, the force of 1 kilogram, okay, and is simply equal to 1 kilogram, okay, and 1 kg, and then 9.8 meters per second squared. So then that will be resulting in the force 9.8 newtons. So the 9.8 newtons. So therefore, a 1 kilogram object will sense the force attraction of 9.8 newtons. Okay, and some students will say, well, okay, 1 kilogram just equal 9.8 newtons. That sort of number-wise is right, but conceptually, mass is the mass. Force is a force. Mass never is, of course. We talk about the dimension. So 1 kilogram, we want the right way to say the 1 kilogram object on the Earth, it will sense 9.8 Newton force. Okay, but it's 1 kilogram object, 1 kilogram object. okay, with mass. If you take that object of 1 kilogram in mass to the moon, it will not sense 9.8 newtons. Instead, it will say like 1 newton, a little more than 1 newton only. But if you take it to Mercury, it will sense like maybe 30 newtons. Okay, but 1 kilogram is 1 kilogram. Number 3, this is another exercise. Just try to familiarize this idea. So acceleration, so how much is the mass, the force? Proportional to the force, 300 newtons. Is like 1 kilogram force is like 9.8, so that's like 30 kilograms. So it's like 60 pounds of force feels like 300 newtons. That's how it. And then 3,000 kilograms, a car, so 3,000. So, and then that, it will give you, so that's heavy, right? So because this big number in there, you get 0.1, okay, and which means 300 newtons is like 60 pounds, pushing on 3,000 3 tons cars, and then that will be, but the object or the car will accelerating very slowly and with this acceleration. So 0.1 meter per second. That means the car will accelerate at this rate, which means its speed will increase 0.1 meter per second every second. Therefore, 0.1 meter second squared. The last question, number 4, is not by Newton's law, but rather it is our simple example of distance, velocity, and time. It's a linear relation between distance and time. So that's non-accelerated motion, the distance. So then the light is a electromagnetic waves, is some energy that travel with time in the space. So, but this formula still apply. The velocity times time, it gives you the distance travels. In this case, how far into space did the signal travel during first 20 minutes? So let's say this is Earth, so this is the antenna, it sends radio waves to the space. How far it goes that way, and it will go this. The distance is equal to velocity is 3 times. So that 0 means this is already in a scientific notation. 0. 8 meters times 20 minutes. So 20 minutes, each minute is 60 seconds. We want to use seconds. So times 60. So make sure that you put the units there, 60. So the number is not our emphasis. Important is the concept. So the answer is, after working through the calculator, I will have 3.6 times 10 to the 10 meters to begin with. Or you always first come up with the standard units, of course, then that's how many meters it goes, okay, in 20 minutes. Very long distance. But if you compare reality how many it is, so then you should compare. That's about 22.2 million, 22 million miles. 22 million miles. Million, I would call it mega. Miles. So miles. So just recap this question. Suppose the radio signal travel from the Earth and through the space at a speed of 3.0 times 10 to the 8 meter per second. How far into space did the signal travel during the first 20 minutes? Well, it travels 20 million miles. Wow, very far. 20 million miles.